We'll now discuss another important concept related to force and momentum, that is the impulse of a force. What is the impulse generated by a force? From experience, you know that if a force stays at the point of action for a longer period of time, you can reduce the pinch of that force. If you want to catch a baseball, I know most of you, if a baseball is moving fast, if you don't want to get hurt, as soon as the ball touches the hand, you move the hand back. Now that will increase the time of contact. Now what does impulse of a force means? Impulse represented by uppercase I of a force is the product of the force and the duration of action of the force. So if a force F Newton acting for a period of time delta t, then impulse I equal to force multiplied by delta t. So the quantity defined as the product of force and the duration of action of the force is what we call impulse of a force. But you know that force is a measure of the rate of change of momentum. Do you remember that? Yes? Force is a measure of the rate of change of momentum. So let's replace the force F by change in momentum divided by that time. So F equal to delta P divided by delta T. Let's replace that. Therefore, the impulse equal to force multiplied by delta T. Force is delta P divided by delta T multiplied by delta T, and delta T's will cancel, giving us a measure of the impulse. Therefore, what is impulse of a force? Impulse of a force is simply the change in momentum that the force has created. The impulse is a measure of the change in momentum that it produces on an object. What is the unit of impulse? The unit of impulse is Newton second. Is that right? Which is the same as kilogram meter per second, because the unit of momentum is kilogram meter per second. The unit of the change in momentum also is kilogram meter per second. Can you show that Newton second is the same as kilogram meter per second? Try that and let me know if you got it right or if you need help. Now, when you drive a nail down, longer the hammer stays in contact with the nail, the smoother will be the drive. I'm sure those of you have tried to drive a nail down. If the hammer gets reflected or deflected quickly, the nail will not go down. In order to drive down the nail, the hammer has to stay in contact with the nail for a certain duration of time, and that will be a smooth driving in of the nail. Well, let's do a small problem. When a 2 kilogram, a 0.2 kilogram baseball is hit, its velocity changes from 25 meter per second to negative 25 meter per second. Well, it goes forward, it is reflected in the back in the exactly opposite direction with the same speed. What is the impulse delivered by the bat to the ball? If the ball is in contact with the bat for 1.1 milliseconds, what is the average force on the ball? Well, in order to calculate the impulse, it is a simple calculation of the change in momentum. Impulse is a measure of the change in momentum. So let's calculate the initial momentum and then the final momentum, and that will help us to calculate the change in momentum. So here the ball is hit on the bat. Therefore, the initial velocity is 25 meters per second and the final velocity is negative 25 meters per second. The mass of the ball is 0.2 kilogram. Its initial velocity is 25 meters per second. Final velocity is negative 25 meters per second. Therefore, what is the initial momentum? Initial momentum is m times vi, that is 0.2 times the initial velocity, that is 5 kilogram meter per second. What is the final momentum? The final momentum is mvf, and vf is negative 25 meter per second. Therefore, the final momentum is negative 5 kilogram meter per second. What is the change in momentum? Delta P is the final momentum minus the initial momentum, that is negative 5 kilogram meter per second minus 5 kilogram meter per second, that is negative 10 kilogram meter per second. Therefore, what is the impulse of that force? The impulse of the force is a measure of the change in momentum. Therefore, impulse is negative 10 Newton second, which is the same as negative 10 kilogram meter per second. Okay, in B, if the ball is in contact with the bat for 1.1 millisecond, 1.1 millisecond is 1.1 times 10 to the negative 3 second. Well, force is a measure of the rate of change of momentum. This change in momentum occurred during this time interval. Therefore, the average force is the change in momentum is negative 10 kilogram meter per second divided by the time is 1.1 times 10 to the negative 3 second. And that is negative 9.1 times 10 to the 3 Newton. Why is that force negative? The force, you see the ball hits the bat and the force is on the ball. The force we have calculated is the force that creates the change in momentum, and that force is the force exerted by the bat on the ball, and that is why it is negative. It is opposite to the direction of the initial velocity. Okay, we will now talk about elastic and inelastic collisions. Alright, I want you to follow the example I'm going to describe, the theoretical interpretations. Momentum P is conserved in all types of collisions. Whenever there is a collision, the momentum is conserved. The total momentum before collision equal to the total momentum after collision. Now, the kinetic energy may or may not be conserved. If you remember, we did a problem in the last class where a truck and a car collides and the system moves together as a single body. And we found that 20% of the kinetic energy was lost. Well, kinetic energy may be conserved or may not be conserved. In most collisions that we are familiar with, kinetic energy is not conserved. Why? Because while colliding, some of the initial kinetic energy gets converted to heat energy, sound energy, and also it is used in doing work in deforming the object. And therefore, for most practical purposes, kinetic energy is not conserved in practical collisions. If no energy is lost in deforming objects, then kinetic energy will be conserved. And that happens only in the minute world where molecules collide with molecules In the room, for example, there are millions of molecules hitting against each other at all times. And these collisions can be considered to be where kinetic energy is conserved, but not in our everyday life. So, if there is no loss in energy during collision, then kinetic energy will be conserved. Alright, watch the definition of elastic collision. A collision where momentum and energy both are conserved is called an elastic collision. So, in an elastic collision, the momentum is conserved, also the kinetic energy is conserved. That means in an elastic collision, no energy is lost in doing work in deforming the objects or producing heat or sound and so on. In gas, when gas molecules collide, it is assumed that the collisions are elastic. No energy is lost in collisions. For an elastic collision, initial momentum equal to final momentum and initial kinetic energy equal to final kinetic energy. It means momentum is conserved, kinetic energy also is conserved. If the final kinetic energy is not the same as the initial kinetic energy, then some energy is lost. Such a collision is called an inelastic collision. So, distinguish between the two. In an elastic collision, no energy is lost. Whereas in an inelastic collision, some energy is lost, so that the final energy is less than the initial kinetic energy. So, for an inelastic collision, momentum is conserved. Momentum is conserved in all types of collisions. But for an inelastic collision, the final kinetic energy will be less than the initial kinetic energy. Okay, let's consider an object of mass m1 moving to the right with a velocity v1I. You are familiar with these notations. There we have an object of mass m1 moving to the right with a velocity v1I. A second object of mass m2 moves to the left with a velocity v2I. Watch that moving. A second object of mass m2 moves to the left with a velocity v2I. They collide and object 1 moves away with a velocity v1f. So they collide. Look at that. The object 1 moves away with a velocity v1f, and velocity of the object 2 after the collision is v2f. So it collides and moves away with the velocity v2f. Okay, I want you to be familiar with these terms. v1I is the initial velocity of object 1. v2I is the initial velocity of object 2. They move towards each other, collide and move away. Object 1 moves away with a velocity v1f, final velocity of object 1. And object 2 moves away with a final velocity v2f. Okay? The momentum of the object 1 before collision. What is the momentum of this object before collision? m1 v1I. And the momentum of the object 2 before collision will be m2 v2I. Therefore, the total momentum before collision will be PI. PI is the total momentum before collision, is m1 v1I plus m2 v2I. Alright, what is the total momentum after collision? The momentum of object 1 after collision is m1 v1f. Momentum of The second object after collision is m2 v2f. So the total momentum after collision Pf is m1 v1f plus m2 v2f. And you know that for all collisions momentum is conserved. That means Pi equal to Pf. Let's write that. Pi equal to Pf means m1 v1i plus m2 v2i equal to m1 v1f plus m2 v2f. Let's rearrange it. I'm going to move the term in m1 to the left and the terms in m2 to the right. So if I move m1 v1f to the left and factor out m1, I will get m1 times v1i minus v1f equal to m2 times v2f minus v2i. I hope you followed that. But all I did is moved m1 v1f to the left, factor out m1 from there, move m2 v2i to the right, and factor out m2 from there. Now, this is the equation that we obtained by considering the conservation of momentum. This is the conservation of momentum equation. Let's now consider the kinetic energy. What is the initial kinetic energy of the two objects? The initial kinetic energy of the first object is 1/2 m1 v1 I squared. Kinetic energy of the second object before collision is 1/2 m2 v2 I squared. So the total kinetic energy before collision is 1/2 m1 v1 I squared plus 1/2 m2 v2 I squared. What is the total kinetic energy after collision? It will be 1/2 m1 v1 f squared plus 1/2 m2 v2 f squared. If the collision is elastic, then Ki will be equal to Kf. So let's take the case of an elastic collision. For an elastic collision, Ki equal to Kf. It means 1/2 m1 v1 I squared plus 1/2 m2 v2 I squared equal to 1/2 m1 v1 f squared plus 1/2 m2 v2 f squared. Well, it looks long, but it is a very simple equation. Let's take this equation to the next slide. There you are. Now, what I'm going to do, first of all, 1/2 exists in every term. I can cancel it. 1/2 will cancel everywhere. And just like I did in the previous case, take the term m1 v1 f squared to the left and m2 v2 I squared to the right, and factor out m1 on the left and factor out m2 on the right. So what does that give you? m1 times v1 I squared minus v1 f squared equal to m2 times v2 f squared minus v2 I squared. Well, to simplify this, we are going to use the simple algebraic factoring, that is a squared minus b squared. I'm sure everybody knows how to factor that. A squared minus b squared is a minus b times a plus b. You see? v1i squared minus v1f squared is v1i minus v1f times v1i plus v1f. Is that right? Factoring difference of two squares. Similarly, factoring difference of two squares here, v2f squared minus v2i squared is v2f minus v2i times v2f plus v2i. Now, if you noticed, if you can watch this in color, well, the colors don't record very well, but if you look at our first equation, what is it? M1 times V1I minus V1F equal to M2 times V2F minus V2I. So this quantity on the left side, M1 times V1I minus V1F, is the same as this quantity on the right side, M2 times V2F minus V2I. That means they can be cancelled. They are the same. Now that leaves us with the simple equation. We have V1I plus V1F equal to V2F plus V2I. Alright? And I'm going to rearrange it. Look at the way I'm going to rearrange it. It is V2F minus V1F. Do you see that? V2F minus V1F equal to, take this to the left. Let me do that for you. Now, it's going to look like this. We have V1I minus V2I equal to V2F minus V1F. Now, on the left, I'm going to factor out a negative sign. That will become negative of V2I minus V1I equal to V2F minus V1F. You see one more time? Take this V2I to the left side, we get V1I minus V2I equal to V2F minus V1F. And then here I factored out a negative sign. You see, negative of V2I minus V1I equal to V2F minus V1F. Alright, that's what this is. Now, what does that actually mean? What is the meaning of V2F minus V1F? And what is V2I minus V1I? Well, let me see if we can have a look at this. Now, here I have the first object of mass M1 moving with the velocity V1I, and the second object of mass M2 moving with the velocity V2I. Now, what does V2I minus V1I represent? Look at that. V2I minus V1I is the velocity of approach. The V2I minus V1I is the velocity of approach. And what does V2F minus V1F represent? V2F minus V1F is the velocity with which they move away from each other. We call it the velocity of recession. So, one more time, V2I minus V1I is the velocity of approach, and V2F minus V1F is the velocity of recession. And what we have here is velocity of recession is negative of the velocity of approach. Now that's an important quantity in collisions. That means for an elastic collision, this is for an elastic collision. For an elastic collision, the velocity of recession, that means the velocity with which they move away from each other, is negative of the velocity of approach. So V2F minus V1F is the velocity with which the two objects move away from each other, and we call it the velocity of recession. And V2I minus V1I is the velocity of approach. Therefore, we make this statement: for an elastic collision, the velocity of recession is the negative of the velocity of approach. For an inelastic collision, now can this equation be modified for an inelastic collision? Yes, we're going to write this with a small modification. For an inelastic collision, the same equation will read like this: V2F minus v1f equal to negative E times v2i minus v1i. The velocity of recession is negative of a constant times the velocity of approach. And this E has a great meaning in objects colliding. E is called the coefficient of restitution between the two colliding objects. So, E, the coefficient of restitution, can now be written as E equal to V2F minus V1F divided by negative of V2I minus V1I. Velocity of recession divided by negative of the velocity of approach. Okay. For an elastic collision, what is the value of E? E is 1. Is that right? For an elastic collision, E is 1. And for an inelastic collision, that will be less than 1. For a perfectly inelastic collision, what is a perfectly inelastic collision? A perfectly inelastic collision is a collision where after the two objects collide, they stick together and move together as a single body. I have actually shown that to you once. Let me show you an example of a perfectly inelastic collision. But before I show you that, what is the value of E for a perfectly inelastic collision? E equal to 0. What does that mean? When E equal to 0, the right side is 0. It means the velocity of recession is 0. They will not be moving away from each other. They will be sticking onto each other. There will be no velocity of recession for a perfectly inelastic collision. Remember our truck hitting a car, and the truck and the car becomes one object? That is an example of a perfect inelastic collision. For a perfect inelastic collision, the value of E equal to 0. That means the velocity of recession is 0. Okay. Now the collision between these two cars, watch the collision between these two cars. You can see this is almost elastic. Almost elastic. Velocity of approach equal to negative of the velocity of recession. Is that right? Yes? There you are. Whereas, let me show you another example where after collision the two objects stick together as one object. You have actually seen this. I'm going to fire this ball into the pendulum. The ball is going to collide with the pendulum, and what happens at the collision? Well, there you are. After collision, the two objects got stuck together and they moved as a single body. So in this case, it is a perfectly inelastic collision and the velocity of recession is 0. Well, you can actually look at collisions in many spheres. Now, I have an object here. I'm going to drop it into this container, and the base of the container is actually steel. So this ball is going to collide with steel. Tell me, if the collision is elastic, what is it that you would expect? If the collision is elastic, there will be no energy lost. That means if I drop it from this height, it must rebound to the same height. But look at this. Most of the energy is lost in that collision. It is a very pitiful inelastic collision. On the other hand, I have a small steel ball here, and watch how this behaves. Can you see this? Now that came almost to the top. You can see here, one more time. it rose up to here. That means it lost very little of its kinetic energy. But still the collision is not elastic. It is inelastic. Well, look at another ball. Well, it lost more than half its energy. That means each of these collisions has a value of E which will be between 0 and 1. Is that right? Okay. So, for an elastic collision, E equal to 1. For a perfectly inelastic collision, E equal to 0. And for most other collision, E has a value between 1 and 0. Let's now talk about kinetic energy in a perfectly inelastic collision. Well, if objects after collision stick together and move as a single unit, the collision is perfectly inelastic. Alright? A trolley of mass m1 is moving with a velocity v1I, collides with a trolley of mass m2 initially at rest, means v2I equal to 0. They collide. After collision, they stick together and has a mass m1 plus m2. Here I have shown that they are sticking together. They have a mass m1 plus m2 and they move away with a final velocity vf. If Ki is the kinetic energy before they collide and Kf the total kinetic energy after they collide, then I can write Ki equal to Pi squared over 2m1. Do you remember in the last class actually we showed that momentum, kinetic energy can be written using momentum. Kinetic energy 1/2 mv squared is the same as P over 2m. So the initial kinetic energy is only the kinetic energy of the first object. The second object has no kinetic energy. So Ki is Pi squared over 2m1, where Pi is the initial momentum of the two objects. And Kf equal to Pf squared over 2 times m1 plus m2, that is the total mass there. And Pi equal to Pf, that means Pi squared is the same as Pf squared. Why? Because in all collisions, momentum is conserved. No matter what kind of collision you consider, initial momentum is always equal to the final momentum. So Pi is always equal to Pf. Therefore, final kinetic energy divided by the initial kinetic energy will be, let me write that down for you. If you want to find the final kinetic energy divided by the initial kinetic energy, it will be Pf squared over 2 times m1 plus m2 times 2m1 over Pi squared. Did you understand that? I want to divide the final kinetic energy by the initial kinetic energy. This quantity divided by this quantity. Dividing by a rational expression is the same as multiplying by the reciprocal. So I took Pf squared over 2 times m1 plus m2 and multiplied it by 2m1 over Pi squared. Is that right? And now, since Pi equal to Pf, these will cancel. The 2 and 2 will cancel, leaving us with m1 over m1 plus m2. And that gives us a very important result. And what does that result mean? When two objects of masses m1 and m2 collide and they join together and move away as a single body, the ratio of the final kinetic energy to the initial kinetic energy is m1 over m1 plus m2. Okay, let's do a problem. A freight car with a mass of 2 times 10 to the 4 kilogram rolls down an inclined track through a vertical distance of 3.3 meter. At the bottom of the incline, on a level track, the car collides and couples with an identical freight car that was at rest. What percentage of the initial kinetic energy is lost as a result of the collision? Alright, let's picture that problem. For a perfectly inelastic collision, we obtained a ratio of Kf over Ki. What is that ratio? Kf over Ki is m1 over m1 plus m2. Now, in this case, the two cars are of identical mass, and this is the mass of one car. Therefore, m1 plus m2 will be twice that value. So, m1 plus m2 equal to 2m1. So, what is Kf over Ki equal to? 1/2. That means, in this particular case, the half of the original kinetic energy is lost. So what is the percentage of energy lost? The percentage of energy lost is Ki minus Kf, that is the amount of energy lost divided by the initial amount of energy multiplied by 100. That will be 1 minus, you see, divided by Ki. Ki divided by Ki is 1 minus Kf over Ki. 1 minus Kf over Ki multiplied by 100. And Kf over Ki is 1/2. So this will be 1 minus 1/2 multiplied by 100. That is 50%. 50% of the original kinetic energy is lost as a result of this collision. Okay. Let's now see how we can calculate the coefficient of restitution when you allow one surface to fall on another surface and rebound. Just the example I showed you. Now consider a ball dropped from a height h1. Alright, this is the floor. A ball is now going to be dropped from that height h1. Now look at that. The ball is dropped from a height h1. Now its initial velocity is 0. Its acceleration is negative g. And it falls through, its displacement is y equal to negative h1 because it is downward displacement. Now if v1 is the velocity of approach to the floor, you see, when you drop an object just before it hits the floor, it will have a velocity. Is that right? That's the maximum velocity. If v1 is that velocity, then we have, that is the velocity with which the ball hits the floor. Then that v1 squared will be equal to v0 squared plus 2ay. Now, v0 is 0, a is negative g, is that right? And y is negative h1. Let's replace that. Therefore, v1 squared equal to 2 times negative g times negative h1. Negative g times negative h1 becomes positive gh1. So, if v1 squared equal to 2gh1, then v equal to square root of 2gh1. If the ball rebounds, if the ball now rebounds with a velocity v2 to reach a height h2, can you write a similar equation for the rebounding process? So the ball has now rebounded. Let's look at that again. After the ball hit the floor, it rebounds, and the velocity of rebound is v2. So that its initial velocity here now is v2, final velocity is 0, is that right? And the displacement y equal to positive h2. So, in a similar way, I can show that v2 equal to square root of 2gh2. Okay, so when a ball is dropped, when I drop a ball, suppose this is the floor, the dropped ball will reach the floor with a velocity v1 equal to square root of 2gh1, and it rebounds to a height of h2. The velocity of rebound will be square root 2gh2. Alright. Since the floor is at rest, remember the collision is between the ball and the floor, and the floor is at rest. v1 is the velocity of approach and v2 is the velocity of recession, isn't it? Since the floor is at rest, the velocity of recession, well, the velocity of approach is v2i minus v1i. And v1i is the velocity with which the ball hits the floor. v2i is 0. Therefore, the velocity of approach simply is v1, the velocity that the ball acquires as it hits the ground. And the velocity of recession is v2. So here we have velocity of approach and velocity of recession right there. And we can use that to calculate the coefficient of restitution. So E equal to V2F minus V1F divided by negative V2I minus V1. That means velocity of recession divided by the velocity of approach. Velocity of recession is V2 and the velocity of approach is V1. Therefore, that is square root 2gh2 divided by square root 2gh1, and that will be square root of h2 over h1. A very simple way to calculate coefficient of restitution between two surfaces. If from a height h1, and after hitting the floor, if it rebounds to a height h2, then the coefficient of restitution between the object and the floor will be square root of h2 over h1. Let's do a calculation of E. Let's calculate the coefficient of restitution between this ball and this steel surface. What all I need to do is, you can see this is graduated. This height is 50 centimeter. So I'm going to drop it from a height of 50 centimeter. My h1 is 50 centimeter. Let me write that. h1 is 50 centimeter. And what all I need to do is measure h2. It rebounded up to 44. So your h2 is 44 centimeter. Therefore, E equal to square root of h2 divided by h1. That will be square root of 44 divided by 50. You don't need to convert the unit because of the ratio. I'm going to leave it for you to calculate that. Let's find the coefficient of restitution between two other surfaces. This is a lead ball. Alright, I'm going to drop it from a height of 50 centimeter. See how much it rebounds. Well, did you get to see how much it rebounded? Well, try it again. Well, it rebounded up to about 5 centimeter. You can see the collision is almost perfectly inelastic. So in this case, the coefficient of restitution is square root of 5 divided by 50. It's a very small value. So this arrangement can be used to find the coefficient of restitution between this surface and any other surface. If you can drop it onto there and measure the height to which it rebounds. We will now do this problem. A dropped ball bounces to 60% of its original height. What fraction of its mechanical energy is lost each time it bounces? What is the coefficient of restitution of the floor ball system? Well, H2 equal to 0.6 H1. That is what this means. It rebounds to 60% of the original height. The final height, the height of rebound, is 60% of the original height. The initial potential energy of the ball, U1, is mgh1. When it rebounds to a height h2, its potential energy U2 is mgh2. And replace that h2 by 0.6 h1. So the potential energy when it rebounds, or the final potential energy, will be 0.6 mgh1. 0.6 mgh1. But mgh1 is the initial potential energy. Therefore, the final potential energy U2 is 0.6 U1. Is that right? Okay. What is the energy lost? Is U1 minus U2. mgh1 minus 0.6 mgh1. U1 is mgh1. U2 is 0.6 mgh1. And therefore, the energy lost is 0.4 mgh1. We want to find the fraction of the energy lost. What is the fraction of the energy lost? The fraction of the energy lost is the energy lost divided by the total energy. If we say 10 students in this class are absent today, and if you ask me what fraction of the whole class is absent, it will be 10 divided by the total number of students. So the fraction of energy lost is the lost energy divided by the original energy. So that will be U1 minus U2 divided by U1. Now U1 minus U2 is 0.4 mgh1, and the original energy is mgh1. Therefore, the fraction of the energy lost is 0.4. If I ask you what is the percentage of energy lost, well, 0.4 is 40%. Okay. Now, E equal to square root of H2 over H1. You can do that right away here. H2 is 0.6 H1. And so that will be square root of 0.6 H1 divided by H1. H1 and H1 cancels. Therefore, E equal to square root of 0.6. That is 0.77. Okay, another problem. A 5 kilogram object with a velocity of 4 meters per second collides head-on with a 10 kilogram object moving towards it at 3 meters per second. The 10 kilogram object stopped dead after the collision. What is the final speed of the 5 kilogram object? Is the collision elastic or inelastic? You can also calculate the coefficient of restitution there between the two collisions. Alright, We got a 5 kilogram object moving with a velocity of 4 meters per second. M1 equal to 5 kilogram. V1I, initial velocity of the first object, 4 meters per second. And we are looking for the final velocity of that first object. What is the velocity of the first object after they collide? We are looking for V1F. And M2 equal to 10 kilogram. V2I is negative 3 meters per second. Why? Because they are moving against each other. If V1I is positive, V2I is negative. It's very important to consider the sign. And V2F is 0. Why? Because after they collide, the 10 kilogram object stops dead. That's the second object. Its final velocity is 0. Alright, since momentum is conserved for all collisions, you know that Pi must be equal to Pf. What is the total initial momentum? M1 V1I plus M2 V2I must be equal to M1 V1F plus M2 V2F. And we have all these values except V1F. We don't have V1F. So 5 kilogram times 4 meters per second, M1 V1I plus M2 V2I is 10 kilogram times negative 3 meters per second equal to M1 V1F. M1 is 5 kilogram, V1F we don't know. And since V2F is 0, this term will become 0. And you notice that here there is only one unknown. Look at that. The conservation of momentum really answers the first part for you. Solving there, you get 20 minus 30 equal to 5 V1F. And that gives you V1F equal to negative 2 meters per second. After collision, the first object went back with a velocity of 2 meters per second. Alright, what's the B part? Is the collision elastic or inelastic? How do you know? Well, we now know that V1F is negative 2 meters per second, and all these quantities we already know. The initial kinetic energy is 1/2 M1 V1I squared plus 1/2 M2 V2I squared. Using these known values, we get the initial kinetic energy is 85 joules. Let's now find the final kinetic energy. 1/2 M1 V1F squared plus 1/2 M2 V2F squared. We have all those values here. Replace these by their values. And that gives you the final kinetic energy is 10 joules. So what's the answer? Is the collision elastic or inelastic? Well, it is inelastic. Is that right? Yes, of course. The collision is inelastic. Let's also obtain the value of the coefficient of restitution here. Well, let me do that for you. What is the definition of coefficient of restitution? We have E equal to V2F minus V1F divided by negative of V2I minus V1I, and that will be V2F is 0 minus V1F is minus negative 2 divided by negative of V2I is negative 3 minus V1I is 4, and that is equal to positive 2 on the numerator, negative 3 minus 4 is negative 7, and negative of negative 7 is 7. So you can see the coefficient of restitution for that collision is 2/7. In any collision, once you are able to obtain the velocities, you can obtain the coefficient of restitution. Alright, let's go and do another problem. A proton of mass m moving with a velocity of 300 meters per second collides elastically head-on with a stationary carbon nucleus of mass 12 m. You know that the carbon nucleus is 12 times the mass of a proton. A. Find the velocity of the center of mass of the system. What is the velocity of the proton after collision? Alright, we got here, this is the carbon nucleus, this is the proton, and the mass of the carbon nucleus is 12 times the mass of the proton. And you know the proton came and hit the carbon nucleus and was rebounded. M1, the mass of the proton is m kilogram. We don't know how much it is. It's enough to say m kilogram. Its initial velocity v1I is 300 meters per second. M2, the mass of the carbon is 12 m kilogram. Its initial velocity is 0. We are looking for the center of mass of the system and V1F. Okay, well, V center of mass is a simple equation. M1 V1I plus M2 V2I divided by M1 plus M2. And we know these values, 300 times 300M times V1I. Well, V1I is 300 and M1 is M. So M1 V1I is 300M. Since V2I is 0, M2 V2I is 0, divided by M1 plus M2 is M plus 12M. And that is 23.1 meter per second. The velocity of the center of mass is 23.1 meter per second. Since the collision is elastic, well, what is the equation for an elastic collision? The velocity of recession equal to negative of the velocity of approach. Alright, so we have V2F minus V1F equal to negative of 0 minus 300. V2I is 0, V1I is 300. So we got an equation for V2F minus V1F equal to 300. Well, can you find the value of V1F from there? No. We're going to say, therefore, V2F equal to 300 plus V1F. Alright? Now, using the conservation of momentum, we need one more equation to solve it because we don't know V2F. Using the conservation of momentum, we have Pi equal to Pf. Initial momentum equal to final momentum. And what's the equation there? M1 V1I plus M2 V2I equal to M1 V1F plus M2 V2F. Let's use all the given values. M1 is M, V1I is 300, so 300M, plus, since V2I is 0, that is 0, M1 V1F, that is M times V1F, plus M2 is 12M times V2F. Now that gives us 300 equal to, since M is present everywhere, we can divide by M. So M will go. We have 300 equal to V1F plus 12 times V2F. Now look at the way I have done here. This V2F has been replaced by 300 plus V1F. So 300 equal to, in this equation, this M has been cancelled. We got 300 equal to V1F plus 12 V2F. So that will be V1F plus 12 V2F has been replaced by 300 plus V1F. Now you have only V1 unknown. Distribute that and solve for V1F. It gives you 300 equal to 3600 plus 13 V1F, and solving for V1F gives you negative 253.8 meter per second. A very good problem. I want you to practice the method that I have used in solving this problem. I know I went through this a little quickly, but I don't think you need a lot more explanation than this. Let me know if you need more explanation. Another one. A 2 kilogram object moving at 6 meters per second collides with a 4 kilogram object initially at rest. After collision, the 2 kilogram object moves backward at 1 meter per second. Find the velocity of the 4 kilogram object after collision. Well, we can use the conservation of momentum. B, find the energy lost in collision. Find the coefficient of restitution for the collision. Alright, let's start by picking the data for the first object. The mass of the first object is 2 kilogram. Its initial velocity is 6 meters per second. After collision, it's moved back with 1 meter per second. Its velocity V1F is negative 1 meter per second. M2 is 4 kilogram and V2I is 0. Is that right? It collides with the 4 kilogram object initially at rest. V2I equal to 0. We are looking for, in the first case, you're looking for V2F. Then we are looking for the kinetic energy lost, Ki minus Kf. And then we are looking for the coefficient of restitution. Alright, how do we find V2F? We use the conservation of momentum. Pi equal to Pf. What is that equation? M1 V1I plus M2 V2I, is that right? There you are. M1 V1I plus M2 V2I equal to M1 V1F plus M2 V2F. Well, we have M1 V1I is 2 times 6. Since V2I is 0, M2 V2I is 0. M1 V1F is negative 1. Plus M2 is 4, we need to find V2F. The only unknown there is V2F. You see how simple the problem becomes? That will be 12 equal to negative 2 times 4 V2F. That gives you V2F equal to 3.5 meter per second. Now, once you have V2F, you can now find the final kinetic energy and the initial kinetic energy. We can find the kinetic energy lost. Ki is 1/2 m1 v1i squared plus 1/2 m2 v2i squared. And how much is that? That will be 1/2 m1 is 2, v1i is 6 meters per second, 1/2 times 2 times 6 squared, plus, since v2i is 0, the second term is 0. And that will be 36 joules is the initial kinetic energy. How about Kf? Kf is 1/2 m1 v1f squared plus 1/2 m2 v2f squared. We have v1f is negative 1 meter per second. v2f we calculated as 3.5 meter per second. And we know m1 and m2. So 1/2 m1 v1f squared plus 1/2 m2 v2f squared. And simplify that, it gives you 25.5 joules is the final kinetic energy. Therefore, kinetic energy lost is Ki minus Kf. is 36 minus 25.5 is 10.5 joules. Can you find the value of E on your own? E is the velocity of recession divided by the velocity of approach. V2F minus V1F over negative of V2I minus V1I. There you are. And we have all these values. V2F is 3.5 meter per second. V1F is -1. V2I is 0. And V1I is 6 meter per second. Put those values in there. It'll be 3.5 minus -1 over negative of 0 minus 6. And you can see that will be 4.5 divided by 6. That is 0.75. Okay, let's now solve one more problem. A puck of mass, just like a hockey puck, mass 0.5 kilogram, moving at 2 meter per second in the positive x direction on ice, collides with a second puck of equal mass initially at rest, V2I equal to 0. After collision, the first puck moves at an angle 30 degrees and the second at an angle -60 degrees. Find the velocities after collision. There is one thing that you need to know. If after collision, if the two objects move away at right angles, it indicates that the collision is elastic. So in this case, if you notice, the first puck moves away at an angle 30 degrees and the second puck moves at an angle -60 degrees, means the angle at which they move away from each other is 90 degrees. Therefore, the collision of the two hockey pucks on the ice is elastic. Okay, there we have M1 equal to 0.5 kilogram, V1I is 2 meter per second I to the right, V1F is at 30 degrees. We don't know the value of V1F. We need to find the value. There, M2 is 0.5 kilogram, initially at rest. And V2F you need to find. You know it is at an angle -60 degrees. So, here comes the first puck. It hits the initial velocity 2 meters per second. It hits the first puck and it goes at an angle 30 degrees. That is V1F. At an angle 30 degrees, and the second puck moves at an angle -60 degrees. There you are. And we now need to find V1F and V2F. Well, we are looking for V1F and V2F. Let's write V1F in the component form. How do you write V1F in the component form? It'll be V1 cos 30I plus V1F sine 30J. So V1F is V1F cos 30 degrees I, its x component, and V1F sine 30J, its y component. Similarly, V2F is V2F cos -60 degrees I plus V2F sine -60 degrees J, the x component, the y component. The momentum is conserved in both x and y direction. Now, when we say momentum is conserved in a collision, it means momentum is conserved in the x direction. That means the initial momentum in the x direction equal to the initial momentum in the initial momentum in the x direction must be equal to the final momentum in the x direction. Similarly, the initial momentum in the y direction must be equal to the final momentum in the y direction. So, conservation of momentum means momentum is conserved in the x direction as well as in the y direction. Momentum is conserved both x and y directions. Alright, using conservation of momentum in the x direction, we have initial momentum in the x direction equal to initial momentum, I'll say it again, initial momentum in the x direction equal to final momentum in the x direction. Alright, what is the initial momentum in the x direction? It is the initial momentum of the first puck. The initial momentum of the first puck is 0.5 kilogram times 2 meter per second I. That is 1 kilogram meter per second I. That is the initial momentum of the first puck. What is the initial momentum of the second puck? The second puck is initially at 0. So the initial momentum there is 0. Therefore, the initial momentum in the x direction is this plus 0, that is 1 kilogram meter per second. This is the initial momentum in the x direction before they collide. The final momentum of the first puck in the x direction is 0.5 kilogram times V1F cos 30 degrees, because the velocity of the first puck in the x direction is V1F cos 30 degrees. Now, the final x momentum of the second puck is its mass times its x velocity, that is 0.5 kilogram times V2F cos negative 60 degrees I. That means if you now add these two quantities, that will be the total final momentum, and that must be equal to the total initial momentum. So PXF, final momentum in the x direction, is this quantity 0.5 V1F cos 30 degrees I plus 0.5 V2F cos negative 60 degrees. Use your calculator to simplify these values. 0.5 times cos 30 degrees is 0.433. So the first term is 0.433 V1F, and the second term is plus 0.25 V2F. So the PXF, the final momentum in the x direction, is 0.433 V1F plus 0.25 V2F. And this must be equal to this quantity, 1 kilogram meter per second. So total initial momentum equal to total final momentum in the x direction. So we got one equation connecting V1F and V2F, looking at the conservation of momentum in the x direction. In the same way, we can now take the conservation of momentum in the y direction to obtain a second equation consisting of V1F and V2F. So using conservation of momentum in the y direction, we have initial momentum in the y direction, PYI, must be equal to the final y momentum, PYF. Now tell me, what is the initial y momentum? Initial y momentum is 0 for both puck. There is no y motion. So PYI equal to 0. Initial y momentum is 0. What is the final y momentum? The final y momentum of the first puck. What is the y velocity of the first puck? V1F sine 30 degrees. So that will be its mass times its y velocity. This is the y momentum of the first puck after collision. What is the y momentum of the second puck after collision? Its mass multiplied by its y velocity, which is V2F sine negative 60 degrees. That means the total final momentum is 0.5 V1F sine 30 degrees J plus 0.5 V2F sine negative 60 degrees J. This is the final Y momentum of the two pucks. And simplifying that gives me 0.25 V1F minus 0.433 V2F. And this quantity must be equal to 0. So we have 0.25 V1F minus 0.433 V2F equal to 0. We have now two equations, equation 1 and equation 2, and I have shown you how to solve equations like this on the calculator. So use the calculator TI-83 or any other calculator to solve this system of equation. It gives me V1F equal to 1.73 meter per second and V2F equal to 1 meter per second. Now that has been a very good problem, and I want you to practice these kind of problems. I know I rushed a bit on this lesson, but a very important and crucial lesson. Please, after listening to the lesson, do all the homework and get back to me if you need any help. Okay, now this ends unit 4. That means you are now ready for, is it unit 4 or unit 3? Unit 3. This is the end of unit 3, and we are now ready for test 3. So go through the practice test and make sure that you understood all the concepts. Very important to know the concepts, and you can solve simple problems. All right? I will see you for unit 4 later on.